Alright everyone, welcome back to your 21st physics lesson, and in this lesson I want to show you guys an example of a gun and a bullet because I think that this is a much more simple explanation of the conservation of momentum. So hopefully I can draw a gun. Let's see how well I can draw it. So here's my gun and here's the barrel, and we'll draw the little trigger right here. Alright, so you know what? I think I'm going to add a handle because this is a pretty good looking gun. Might as well keep it going. So there is your gun right here, and inside the gun you have a bullet. Now a bullet usually looks something like that, and my bullet my bullet looks a little bit like something else. But anyways, this is a gun and that is a bullet. Let me go ahead and label this. You probably can't even see that. Bullet and gun. For some reason, I really like labeling things. And gun. So let me go ahead, and the only other thing I want to do is write the formula for momentum, which is momentum. There we go. That's how you spell it. Mass times velocity. Now I want to write this down because it's pretty important, and I'm going to keep referring to it in my example. So right now, like I said, let's go ahead and figure out the total momentum of the system. Well, you guys are probably saying, wait a minute, okay, what's the mass of the bullet? What's the mass of the gun? You know what? It doesn't matter because the velocity of this entire system is zero because obviously it's not moving. You're not, doing a drive-by or anything. So since the velocity is zero, no matter what the mass is, the momentum has to be zero too. So just remember that the total momentum of the system is zero before the event. Now the event, of course, is the firing of the gun. Now whenever the gun gets fired, this bullet goes zooming out here at an extremely high velocity, and I'll symbolize that by writing up arrow velocity, or V. Now, in addition to the high velocity, in comparison to the gun itself, this bullet is just a little piece of metal. So therefore, it has a very low mass. And I'll symbolize that by writing down arrow mass. Now, whenever you fire a bullet, it's not like the bullet only moves and that's it. There is a little bit of kickback in the gun. Now, whenever there is a kickback in the gun, a couple things are happening that we need to take note of. First of all, it kicks back in an opposite direction, and in comparison to the bullet itself, the gun is this big chunk of metal, so it has a very high mass, and in comparison to the speed or velocity of the bullet, it has a very low velocity. Of course, the kickback itself isn't as fast as the bullet flying through the air. So let's go ahead and look at this again. Two things are causing momentum. First of all, the bullet, which has a high velocity and a low mass, and second, the gun, which is kicking back in the opposite direction, and this has a high mass but a low velocity, so pretty much the opposite of the bullet. So in this case scenario, and in every case scenario, whenever you fire a gun, momentum is conserved. Therefore, the total momentum of the system is zero after. Why is this the case? Well, even though we don't know the exact mass of the bullet or the gun, we know that the bullet and the gun both have momentum, but their momentum is pretty much moving in opposite direction, so they cancel each other out. Why did they cancel each other out? Well, like I said, because they're moving in opposite directions, and the momentum of both the bullet and the gun is always going to add up to zero. So there is probably a more simple explanation using a gun and a bullet because, you probably are going to fire a gun more often than you're going to tie two carts together with a spring and a rope and cut them. So hopefully you guys understand about the conservation of momentum now. And yeah, that's all I got to say about that. So thank you guys for watching, and I'll see you guys in the next video.